Lesson 64. Lesson 64 is going to give us another type of variation in mathematics, and this one is called inverse variation. And that's why all of our bell work today is about direct variation, which can be written as y equals mx. All right? Now, y equals mx, one of the things that we pointed out was that if we solve that for m, y'all pay attention, this is extremely important. If we solve that for m, in other words, if we wanted to find the direct variation, we divide both sides by x, and our constant of variation is always going to be y divided by x, right? That's how we find our constant of variation, is dividing y by x. What's 9 divided by 3 here? It's 3, right? So 9 divided by 3 gives us our constant of variation. What is 4 divided by negative 8? Negative 1/2, and that's why we said that negative 1/2 was the constant of variation. All right? So we can always find the constant of variation in direct variation by y divided by x. So m equals y divided by x is equivalent to y equals mx. And both of these are forms of what we call in mathematics a direct variation. Y varies directly with x. Okay? Direct variation. What we're going to learn today is inverse variation, and inverse variation is confusing, makes direct variation more confusing if you don't have a solid way of knowing the difference. What's direct variation? Y equals something times x. How do you find the something that's times x? With y divided by x. All right? That's direct variation. Y divided by x equals the rate of change. Yes?
Have you done uncertainties?
Yeah, we'll do that later. All right, today we're going to be looking at inverse, not operations. That should be inverse variation, not vation. Should be writing. If you don't get these definitions, y'all, you're going to be lost. These tests, because we're getting more and more new terms, right? Direct variation was a new term for us. Inverse variation is a new term for us. So if we don't know those two terms and definitions very well, then we're going to get confused when we're told to write a direct variation or write an inverse variation. And you're going to call it, because there's direct variation, we're going to want to call it indirect. But it's inverse variation. Okay? All right. Here's the definition. Inverse Inverse variation is a relationship between two variables whose product is a constant. X times y equals k, where k is a constant, is an inverse variation. It can also be written as y equals k divided by x, which I prefer. I really like writing my fractions in this form, k divided by x. And of course, if we cross multiplied this expression, what would we get? X times y equals k. All right, so our two variables are x and y as normal, because most of the stuff that we do in mathematics is in the xy plane. So x, this is the good old x-axis variable, and y is the good old y-axis variable if we're thinking about this graphically, and that's exactly what we're going to do toward the end of the lesson. Inverse variation is a relationship between two variables whose product is a constant. For example, x times y equals k, where k is a constant, is an inverse variation. It can also be written as y equals k divided by x. All right? So what was the other? This is inverse variation. X times y equals k, or y equals k divided by x. Right? What was direct variation again? Y equals m times x, which is also written as y divided by x, is always the same thing. All right, so direct variation is where you divide y by x and you always get the same thing. Inverse variation is where you multiply y times x and you always get the same thing. All right, so let's look at an example of direct variation. Direct variation we're used to, right? We just looked at 3, 9, 2, 6, 8, 24. What's the direct variation that's represented here? Y equals 3 times x. Okay, that's a direct variation. Here's an example of an inverse variation. What's the inverse variation here? X times y equals 6. What do you get if you multiply all of these x values by all of the y values in the pair? You get 6, right? Negative 2 times negative 3, 6. 1 times 6, 6. Negative 6 times negative 1, 6. 3 times 2, 6, right? What else could we put in there that would work? Any other solutions that y'all could think of there? How about x equals 1/2, y would have to be what? 12. Okay, x equals 18, y would have to be 1/3. Yeah, so you get it. That's the relationship of an inverse variation. Okay, in each of these problems up here, y divided by x equals 3. In each of these problems down here, each of these, well, not problems, but each ordered pair in this example, y times x is equal to 6. Right? So direct variation is y divided by x is always the same thing. Inverse variation is y times x is always the same thing. All right? So let's have a look at this one. Tell whether each of these relationships is an inverse variation or not, and explain. Is y divided by 6 equals x an inverse variation? No? What is it?
It's a direct variation.
If you cross multiply, what would you get here?
6.
Y equals 6x.
Direct variation.
That's direct variation, right? All right. Is this an inverse variation? Letter B.
Yes.
Yes. X times y equals 5 is an inverse variation because x times y is the same thing every time. What are some solutions to it?
2 and 2.5.
2 and 2.5. Very good.
And
2.5 and 2. That's 1. 1 and 5. 5 and 1. Negative 1. Negative 5. Negative 5. Negative 1. Somebody said 1/2 and 10. So we can talk about the solutions to these as well. The solution to any relation is an ordered pair that makes the relation true. So these inverse relations, and we're going to examine the graphs of one of these in just a minute, and you're going to see that every direct variation looks very similar, right? Every direct variation is what? It's a line through the origin, right? Has a slope, a y-intercept of 0. Yes?
On A, could you not multiply y times itself and then multiply it to the other side and get 6 equals xy?
You have to divide 1.
What did you just say? Well, the short answer is no, but I want to understand what you said, and so I can do it.
When you do something to an equation to solve it,
Yeah.
you multiply y times itself, or would you have to divide it?
You'd have to multiply both sides by y, and you'd get y squared over 6 equals xy.
Oh, okay.
Okay, so you could multiply both sides by 1 over y. All right? If you multiply both sides by 1 over y times this side, 1 over y times this side, then you get these y's canceling. You get 1/6 equals x divided by y. X divided by y is, that's direct variation. Because if you reciprocate both sides, what do you get? Y divided by x equals 6 over 1. So this is direct variation by definition.
Cross multiply.
Right, you get y equals 6x again. So no matter what you do mathematically, as long as you don't make an error or break rules, you're going to get direct variation out of letter A, and you get inverse variation out of letter B. Okay? All right, next example. Now we're being told, and these problems throw students off. Now I'm warning you about Unit 7 test. This is a commonly missed problem on the Unit 7 test. If y varies inversely as x, what does that tell us we're dealing with? Inverse variation, right? What is inverse variation? X times y is always the same thing, right? And then it goes on to tell us something else. All right, so we got our first part of our word problem. Y varies inversely as x. That means x times y is always going to have the same product. And look at this. They tell us that y equals 3 when x equals 12. Why do we multiply them together? Because that's what inverse variation does. Inverse variation is the product of x and y. So x times y equals 36. That's the specific inverse variation that we're dealing with here. All right? Now, find x when y equals 9. If y equals 9, x has to be 4. 4 times 9 is 36, in the same way that 3 times 12 is 36, right? Find x when y equals 6. 6 in this inverse variation. We got to multiply x and y to get 36. So inverse variation, and I know this seems really, really easy to you guys right now. But when you're looking at a problem on a test, problem number 6 is talking about direct variation. Problem number 7 turns around and talks about inverse variation. It gets very confusing. Okay? So make sure you know how to distinguish between the two. Write an inverse variation relating x and y when x is 3 and y is 8. Inverse variation. X times y equals something, right? What would x times y have to be in this specific inverse variation? 24. All right. How would you write that in in the other form of inverse variation? Y equals 24 divided by x. All right? Y'all okay with that? Find other x and y values that represent this inverse variation and graph the relation. All right, so we're dealing with x times y equals 24. We got 3 and 8. Y'all slow down. I just said 3 and 6, right? 3 and 8. 2 and 12. Yeah, I don't really want to graph 2 and 12, but we'll look at it. 6 and 4. 1 and 24, I'm definitely not going to draw a graph of, but it would work. 8 and 3. 4 and 6. And then we could do the negatives of all these, couldn't we? All right. I'm confused why y'all aren't writing this down. Again, you're allowing this to lull you to sleep, that it seems easy. -4, -6. Right? That's a bunch of points, isn't it? There are an infinite number of points that would work here. Yeah. Half of 48. 1/3 of 72. Okay. 1/5 of 120. I mean, there's an infinite number of points that you can multiply, or infinite number of numbers that you can multiply together to get 24. So it's an infinite set. The solution set here is infinite, just like the solution to a line, right? Okay, so let's have a look at these points. Let's do this. Let's have a look at these points that represent this direct variation, inverse variation, y equals 24 over x. This is going to be a very rough sketch because I'm not going to take the time to do a lot of grid lines and things, but all right. Let's start with 212. This is going to be somewhere up here. All right. 3/8 is going to be just below it. 4/6 is going to be just below that. All right. 8/3 is going to be just below that. What else? 212. We didn't put 12/2 up there. 12/2 would be somewhere like right in here. So it's going to have a nice sloping curve like that. Right? If we went all the way over here to, let's see, 48, x is 48, y would have to be 1/2, right? So it's getting closer and closer to the x-axis, right?
What about the
It
negative?
never touches it, right? Yeah, so the negative values are going to do what? If we put the negative values on the graph, we would have, let's see, -8, -3, -12, -2 would be somewhere over here. Forgive me for the scale of this. -8, -3, -4, -6, -2, -12. You know, it's going to do exactly the opposite kind of curve on the opposite side. All right, so that's what our inverse variation is going to look like, right? Grab your graphing calculator. Now, if you put this into your graphing calculator, you can't put it in as x times y equals 24, right? Because your graphing menu is y equals, so you have to solve and get it in y equals 24 divided by x form in order to graph it.
Is that still called inverse variation form?
Do what?
Is it like a certain form, or is it still called inverse variation? When it's in
Yeah, it's inverse variation still. Still x and y have an inverse relationship. All right, so is everybody, your graph should confirm that it looks like this, right? Now, go back into your graph and change that to, actually, do a second one. Instead of 24 over x, do a second graph, y equals 10 over x. Now, this is a separate inverse variation.
The zoom.
X times y equals 10.
Gets closer. Ooh.
Zoom 6 if you want to standardize your screen. Zoom, option 6, standard zoom. Okay. Yeah, that one's just going to be inside of it, right? So it's the same basic shape, but y equals 10 over x is going to be inside the other one like this, right? And if you went all the way down to what your parent function for this is, the parent graph is just y equals 1 over x. Y equals 1 over x is going to be even closer to the origin. But what do you notice about the general shapes of these graphs?
They're like boomerangs.
They're like boomerangs. Yeah? Right, so they all have the same shape, right? They're just being kind of sucked in toward the origin. Symmetry-wise, they have a symmetry to the line y equals -x, but that's not what we're talking about today. But there is a symmetry to these graphs. Okay? All right, now this is the first time that we can kind of give meaning, y'all pay very close attention to what I'm going to say, to an excluded value for x. If y equals 24 over x, what value is excluded for x? Yeah, x cannot equal 0, right?
There's no x-intercept.
If x cannot be 0, there's no y-intercept. All right? If x can't be 0, the y-intercept is defined to be where x is equal to 0. So that value there is called an asymptote.
Why can't be 0 either, right?
That's exactly right. In this particular relationship, y cannot be 0. Because you can't take 24 divided by something and get 0. You can't divide by something and get 0 unless the number you're dividing is 0. And x times y equals 0 is a very boring inverse relationship, right? Okay. All right. So x equals 0 is what we call an asymptote. It's a vertical asymptote. And in this particular case, somebody pointed out that y cannot be 0 either. Y equals 0, which in this case is the x-axis, is also called an asymptote. Right? This is something that you're going to have to know eventually. All right. It's an asymptote because by property, by nature, these two graphs are going to get closer and closer to the x and y axis, but they will never touch. All right. So as x approaches infinity and as y approaches infinity, they get really, what the word is infinitesimally close, but it never touches. This keeps getting a little bit closer and a little bit closer and a little bit closer and a little bit closer. All right. So that's that. Any questions about the graphs or sketching the graphs of what these look like? Yes, ma'am. As long as it's a straight up direct variation, inverse variation, it will. Now we can vary these, and we can talk about something like this: y equals 15 over x minus 1, for example. Now, what is the x minus 1? What's the excluded value going to be for that one? X cannot equal 1. And if you put this in your graph, put it in your graphing calculator. Make sure you use parentheses for your denominator. Y equals 15 divided by x minus 1. You're going to notice that the shape is very much the same, but it's no longer centered around the origin. The asymptote is x equals 1 now, the vertical line x equals 1.
It's like in the middle.
Yeah. And this one does have a y-intercept. Why? Because x can be 0. If x can be 0, then we're going to have a y-intercept. And if you wanted to see even more of an exaggeration, go back into the same thing and do y equals 15 over x minus 4. And then you'll see it shift way over to the right, right? That's what your graph will show in your graphing calculator. All right. So, but this is no longer an inverse variation, because the inverse variation is x times y equals a constant. Like this is inverse variation. Y times x minus 4 is not an inverse variation. It is a translation of an inverse variation 4 units to the right. And we're going way beyond what we're going to be talking about initially, but you can kind of start thinking about and playing with what a graph does when you change certain parameters in it. Yes?
You know, like how they go like that? Well, where do they like meet? You know what I mean?
Where do what like meet? The x and y axis?
Yeah. Or no, where do these two meet?
They never meet.
But they're one line.
No, it's one relation.
They never meet because one goes this way, but they never cross the x-axis.
Okay, let's go back. Let's go back. Y'all listen. Let's go back to what we were initially talking about. I don't know where we are at this point. 15 over x minus 4 maybe is the one you're talking about, right? It's broken at x equals 4.
So we can't go past that.
It's broken there. It doesn't exist there. It's called, the mathematical term for it is a discontinuity. The function is not continuous. There's breaks in it. Skips, jumps, holes, those are all breaks in functions. Okay? This one is broken at x equals 4. X can't be 4. That would be division by 0, which is undefined. So that's why we see that break at x equals 4. All right? It's also broken because x can't be 4. This expression over here can never take on a value of 0. 15 divided by something can never be 0, right? 15 divided by something can never be 0. So y is not equal to 0. That's broken there also. Y equals 0 is the x-axis. If you don't believe me, go into your graphing calculator and put in y equals 0. It's just going to graph the x-axis. Okay? So it's broken there, which means it's never going to intersect that line also. Okay? And that's just kind of the things that you guys are asking great questions and analyzing this relationship. And that's one of the great parts of this graphing calculator. You can just play with it and, see what happens if you do this, see what happens if you do that. All right? All right, let's move on. Next example. A truck driver is delivering goods from one state to another. See how many of y'all thought it was a her when you started reading the problem? Y'all are all sexist. You all assumed it was a man.
It's not sexist.
Yes, it is.
Hey, if there's no general,
Stereotypical.
Yes.
I have a.
Sexist or
If
stereotypical?
it does not say the thing at first, you're always supposed to assume the masculine.
Which is dumb, but whatever.
All right, a truck driver is delivering goods from one state to another. Her speed is inversely related to her travel time, right? She is traveling at 55 miles per hour. It takes her 13 hours to reach her destination. All right, so what does this say? Her speed is inversely related to her time.
So speed is
Okay? Speed is rate times time equals distance, right? So this is an inverse relationship. In this particular D equals RT, R and T are inversely related to one another. Distance is directly related to rate and time. Okay? So we're treating distance as a deal. And why is distance in this thing constant?
because you can't have.
Because the states aren't moving, right? She's moving her goods from one state to another. The distance is fixed. The distance between Jackson, Tennessee and Memphis, Tennessee is not changing very much at the moment. Okay? All right. So the rate times the time is equal to some distance. All right. How are we going to change that distance? Or how to figure out what that distance is? Well, they tell us that her speed is inversely related to her travel time. So what do we need to do to speed and time? Multiply. Okay? Her speed is 55. Right? I said 55 and wrote 15. Her travel time is 13 hours, which means her distance is... Y'all all have calculators and you're staring. 715. So the relationship that we're working with here is her rate times her time will always be 715 miles. How long will it take her to travel? How long will it take her? That's time, right? Find T when R equals 65. So you make the substitution. R is 65. You divide both sides by 65, and it'll take her 11 hours if she travels at 65 miles per hour. So that's a big difference, right? 10 miles per hour difference saves her 2 hours on the trip. Yes?
So if it says that it's inversely related to blah, 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 blah.
You multiply the two quantities.
But are you going to count off if you don't write down the formula?
You know, I always like you to do that. I'm not going to count off if you don't, but I'm going to tell you that it's really good practice to always write the formula that's being used. Okay, it's just good practice. It's going to keep you from making mistakes on tests, right, Bo? Writing that formula down, knowing the formula and writing the formula is going to help you make fewer mistakes. It also solidifies the formula for you. Does that help answer your question? All right, homework.